So in the last video, I just covered simply distributive loadings and how to replace our supports here with reaction forces. In this video, we're just going to do an example. So our example says find the support reactions at A and B. Now this can look a little overwhelming, so let's redraw this with the forces in replacement of our supports here. So if we remember, our A here, this is a pin connection, and this is roller. So our pin connection has a X force and a Y force, and our roller here only has a Y force. So let's redraw that. So this, at the end we have A, so we have force in the Y direction going up, so I'll call that AY. We have force in the X, AX. Then there's a distributive load across here. We have a moment right here. And around here, we have our rollers, so we replace that with BY. Right, and then there was a point force at the end here. So let's add the magnitudes. So we have 25, 12, and 25. So our point force is 25 kilonewtons. We have 12 kilonewtons per meter here, because this is a moment, not a point force. This is a moment at this point, and call this point at the end here C. And our distributive loading was 25 kilonewtons per meter. So now that we've replaced our our supports with their reactions, let's replace our distributive loading with a point force. Okay, so now that I've drawn in the dimensions, we can use these dimensions to first reduce this simply distributive loading into a force resultant. So given a distributive loading, the force resultant is equal to the area of our shape. So our shape's a rectangle, so it's equal to length times width. So the length is 2 meters multiplied by, we have the width here, or you can say height, is 25 kilonewtons per meter. So 25 kilonewtons per meter. Meters cancel there. We have 2 times 25, and that's 50, and we get 50 kilonewtons as our force resultant. So let's erase our distributive loading and replace it with a force resultant. So we have to figure out where we are going to place it first. So since it's a rectangle, the midpoint of this force resultant is just the length of the rectangle, so 2 meters divided by 2. So it's at 1 meter. So we're going to place it at 1 meter from point A. So going right from the left, right? So let's do that. Okay, so 50 kilonewtons is our force resultant. Now let's get rid of this to clean it up a little bit. Now we have to use our equilibrium equations to find each of the forces. So let's do the x direction first. So the sum of Fx is equal to 0. 0 equals 2, and now let's find all our x forces. Oh, we only have 1, right? So Ax is equal to 0. And that's it. That is our only x force, and we don't need it. So let's get rid of it. We can actually get rid of Ax off our diagram here. See how we reduced this mess into just a very simple looking free body diagram here. So now we do the sum of y forces. Say up is positive, and we have 0 is equal to, so we have AY minus the 50 kilonewton resultant force from our distributive loading. Okay, that's a moment, so we don't care about that. It's not a force. And then, well, it's not a force we need. And we have By, so plus By, and then minus 25 from this point load at the end of our beam here. So we've run into an issue. We have two unknowns, Ay and By, but we only have one equation. The equilibrium equation for the x direction didn't really help us, did it? So how are we going to do this? Well, that's where our moment equation comes in. So the sum of moments is equal to 0. Now, where are we going to take this moment? Now, let's take this moment at point A. And since we took it at point A, we are not going to include the moment at A. You see how that reduces our unknowns to only one, because AY is not needed, and we just use BY. And then we can solve for BY in our moment equation and sub it into our other equation to get AY. So let's remember what the formula for a moment is. I'm going to write it in the top left corner here as a reminder. The moment about a point, so we'll say point A, is, well, I'll say point B because we're not going to use point A in this problem. I don't want to confuse. So point B is equal to the force at point B multiplied by the perpendicular distance to the point of interest. And our point of interest is A. So 0 equals, and let's start at A here. So we don't include A. Now we've run into a force. So force is 50 kilonewtons. And what is its distance to A? 1 meter, right? So times 1 meter. And also we forgot to set our coordinate system. So I want clockwise to be positive. And the way you can think about this is we have A here, and A is now kind of like a door hinge. You can rotate it. So how is the 50 kilonewton force rotating it, right? It's rotating it this way, and that's clockwise, and that's what we set positive. So our 50 kilonewton force times 1 meter is positive. Next, we move on to our moment here that we're given. Since it's a moment already, we don't have to multiply it by the distance. As you can see, we already have it multiplied by meters because it's a moment. So we just add it on, but actually it's going in the counterclockwise direction. So we subtract 12 kilonewtons here times meters. And then our last force, or sorry, we have two more. We have By. By is how many meters away? It is 4 meters away from A, right? And where does By taking A? It's taking A counterclockwise. So that's minus By, so that's the force By multiplied by the distance, 4 meters. And then our last force here is our 25 kilonewton point force. That is the entire length of the beam. So it's going clockwise, right, this way, so it's positive. So that's plus 25 kilonewtons times how many meters? 6 meters, right? So let's simplify this and solve for By. Now let's solve for By. So 4By is equal to, we have 50 minus 12 plus 150. So that's 200 minus 12. So 188. Solving for by, I'm going to scroll down real quick. Solving for by, we have 188 divided by 4, and that's 47 kilonewtons. So we got our force. So let's get rid of our moment here. And so we found that By is equal to 47 kilonewtons. We used the moment about A to do that, right? So let's replace that on our free body diagram. 47 now. Oh, that's terrible. And now we only have one unknown, right? So let's replace that in our equation here. 47. So solving for AY is equal to, we have 50 minus 47. I'm moving these to the other side, right? So we're changing the sign. So 50 minus 47 plus 25. So this is equal to 25 plus 50 is 75. And then 75 minus 47 is 28. So AY is equal to 28. And let's erase all of this. So we have By and AY, and we also found that our force resultant from our distributive load was 50 kilonewtons. And that's it. Now we can replace this. So 28 kilonewtons. So we went from this, let's analyze this. We went from this to this. And how did we do that? First, we redrew it in a more concise way by replacing our supports here with reaction forces, right? We replaced B with a upwards force, and then A with a force in the X and the Y, but our X was 0, so we got rid of it. Then we took this distributive loading and we reduced it by getting the magnitude and then finding where it was placed on our beam. And then we used our equilibrium equations to solve for the missing values. And that's it. Thanks for watching this video. If you're confused on how to find reaction forces or reduce distributive loadings, just watch my other 2 videos on it. But anyway, have a great rest of your day. Also, if you hear heavy breathing in this video or sniffling, it's because I'm sick and I'm sorry.